Good day everyone, my name is Nurakman M. Gandamra and my topic is changes in constraint quantity values. The second type of sensitivity analysis that I will discuss is the sensitivity ranges for the constraint quantity values. That is, the values to the right of the inequality signs in the constraint. For our Beaver Creek Pottery Company model, maximize Z is equals to $40 x sub 1 plus 50 x sub 2 subject to x sub 1 plus 2x sub 2 plus s sub 1 is equals to 40. For x sub 1 plus 3x sub 2 plus s sub 2 is equals to 120. X sub 1 and x sub 2 is greater than or equal 0. The constraint quantity values are 40 and 120. Consider a change in which the manager of the pottery company increases the labor hour from 40 to 60. Increasing the labor hour from 40 to 60 causes the feasible solution space to change. Let's have a look on this figure. As you can see, the x sub 1 and x sub 2 has a value. That is because it is already given. So the thing that you should do is to interpret their values by plotting them in the graph. This thing should be easy for us, since we learn how to plot when we are in high school, right? In this graph, it is already plotted. The next thing for us to do is to find the value of z. Let's go back to the first formula. This formula, substitute x sub 1 and x sub 2 to their corresponding numbers. You'll get an answer of $1,680. But the answer here in the graph is wrong. It has some technical error, so the answer should be $1,680. In the next problem, the answer is $1,360. However, the important consideration in this type of sensitivity analysis is that the solution mix, including slack variables, did not change, even though the values of x sub 1 and x sub 2 did change. The focus of sensitivity analysis for constraint quantity value is to determine the range over which the constraint quantity values can change without changing the solution variable mix, specifically including the slack variables. Following is, if the quantity value for the labor constraint is increased from 40 to 80 hours, the new solution space is OAC, and a new solution variable mix occurs at A, as shown in figure 3.7a, which will be shown later. Whereas at the original optimal point B, both x sub 1 and x sub 2 are in the solution. At the new optimal point A, only x sub 2 is produced. Thus, the upper limit of the sensitivity range for the quantity value for the first constraint, which we will refer to as q sub 1, is 80 hours. Furthermore, as q sub 1 increases past 80 hours, s sub 1 increases. Similarly, if the value for q sub 1 is decreased to 30 hours, the new feasible solution space is OAC, as shown in figure 3.7b, which will be shown later. The new optimal point is at C, where no mags are produced. The new solution is x sub 1 is equal to 30, x sub 2 is equal to 0, s sub 1 is equal to 0, s sub 2 is equal to 0, and z is equals to $1,200. In summarizing the sensitivity range for the constraint quantity value for labor hours, we will use 30 is less than or equal q sub 1 is less than or equal to 80R. Now let's have a look at figure 3.7. In this figure, there are two graphs, namely A and B. The only thing that you will do here will be interpreting the values and plotting them in the graph. Next is about the sensitivity range for clay. If the quantity value for the clay constraint for x sub 1 plus 3x sub 2 is less than or equals to 120, is increased from 120 to 160, then a new solution space OAC results with a new optimal point C. If the quantity value is decreased from 120 to 60, then the new solution space is OAC. The new optimal point is A. In summarizing, the sensitivity ranges for Q sub 1 and Q sub 2 are 30 is less than or equals to Q sub 1 is less than or equals to 80 hours. 60 is less than or equals to Q sub 2 is less than or equals to 160 pounds. So let's have a look on figure 3.8. As you can see, this figure also has two graphs, which is A and B. These sensitivity ranges are valid for only one Q sub 1 value. All other Q sub 1 values are assumed to be held constant. These ranges for constraint quantity values provide useful information for the manager, especially regarding production scheduling and planning. If resources are reduced at the pottery company, then at some point, one of the products will no longer be produced, and the support facilities and apparatus for that production will not be needed, or extra hours of resources will be created that are not needed.
Good afternoon, everyone. Today, we are going to talk about the last model parameter of sensitivity analysis, which is the constraint quantity value ranges with Excel and QM for Windows. The constraint quantity value ranges with Excel and QM for Windows are expressed in the term of allowable increase and decrease to better understand the flow of sensitivity ranges. In this report, shown the sensitivity ranges for the constraint quantity value which are expressed in the form of allowable increase and decrease. While this report shown the sensitivity ranges for the constraint quantity value with QM for Windows showing the Beaver Creek Pottery Company solution. To better understand that, we have here a known example, Beaver Creek Pottery Company. For instance, in our Beaver Creek Pottery Company example, a new, less experienced artisan were hired to make pottery. It might take this individual 1.33 hours to produce bowl instead of 1 hour. The labor constraints for this problem will change from x sub 1 plus 2x sub 2 is less than or equal to 40 to 1.33 x sub 1 plus 2x sub 2 is less than or equal to 40. So, take note na sa pagpapalit natin ng coefficient ng x sub 1, mapapalitan yung solution from OABC to OAC. It will result in new optimal solution for maximizing the problem, which is the x sub 1 equals to 30, x sub 2 equals to 0, and z, or the total profit, is equal to 1,200. The result will be like this. Maximized profit is equals to 40 pesos x sub 1 plus 50 pesos x sub 2, subject to 1 x sub 1 plus 2x sub 2 is less than or equal to 40, while 4x sub 2 plus 3x sub 2 is less than or equal to 120, which is the original value for labor and clay. X sub 1 and x sub 2 is greater than or equal to 0. And 1.33 hours would be the upper limit for this constraint coefficient. However, mga ganitong uri ng sensitivity analysis ay hindi karaniwang binibigay sa mga standard linear programming computer output. So, ang ginagawa nila is to run the computer programming with different values to identify the effect of this type of change. Moving on from other forms of sensitivity analysis, which are to add any constraints to the model or to add a new variable. For example, suppose the Beaver Creek Pottery Company add a third constraint for packaging. It's pottery. The third constraint would be as follows. 0.20 x sub 1 plus 0.10 x sub 2 is less than or equal to 5 hours. This would require the model to be solved again with a new constraint. This new constraint does, in fact, change the optimal solution. As shown in Exhibit 3.15, this spreadsheet requires a new row of 8 added to the original spreadsheet. So as you can see, meron na tayong new constraint to Beaver Creek model with 0.20 x sub 1 plus 0.10 x sub 2 is less than or equal to 5 hours of packaging. Meron tayong original solution na 24 bowls, 8 mugs, and 1,360 of profit. Ang new solution natin is 20 bowls, 10 mugs, and 1,300 profit. In the equation 4, maximize Z is equal to profit per unit for bowl 40x sub 1 plus profit per unit for mug 50x sub 2. Subject to number of hours for labor, 1x sub 1 plus 2x sub 2 is less than or equal to 40. Then number of pounds of clay, 4x sub 1 plus 3x sub 2 is less than or equal to 120. Then for packaging, 0.2 x sub 1 plus 0.1 x sub 2 is less than or equal to 5. Then x sub 1 and x sub 2 is greater than or equal to 0. Let's proceed to adding new variable. This will also require to be solved again to determine the effect of the change. For example, suppose the pottery company were contemplating producing a third product, cups, requiring 1.2 hours of labor and 2 pounds of clay. It can secure no additional resources and the profit per cup is estimated to be 30 pesos. This change is reflected in the following model reformulation. Maximize Z is equal to profit per unit of bowls 40 pesos x sub 1 plus profit per unit for mugs 50 pesos x sub 2 plus profit per unit for the cups 30 pesos x sub 3 subject to x sub 1 plus 2 x sub 2 plus 1.2 x sub 3 is less than or equal to 40 hours of labor. 4x sub 1 plus 3x sub 2 plus 2x sub 3 is less than or equal to 120 pounds of clay. Then x sub 1 and x sub 2, then x sub 3 is greater than 0. Ibig sabihin nito, this solving model shows that change has no effect on the original solution. The model is not sensitive to this change. The estimated profit from cups was not enough to offset the production of bowls and mugs, and the solution remained the same. So that's it. I hope you understand. Good
Good day everyone, my name is Fatma Al Compania and today I'm going to explain the shadow price and how to compute shadow price. Shadow prices. In linear programming problems, the shadow price of a constraint is the difference between the optimized value of the objective function and the value of the objective function evaluated at the optional basis. When the right-hand side RHS of a constraint is increased by 1 unit. So here's the example of the calculation of shadow prices. First, we have to solve the LP problem and determine the optimal solution. For constraint 1, when x1 is equal to 0, x2 is equal to 6, and when x2 is equal to 0 and x1 is equal to 3. For constraint 1, when x1 is equal to 0, x2 is equal to 4, and when x2 is equal to 0 and x1 is equal to 4. For constraint 3, when x1 is equal to 0, x2 is equal to 2, and when x2 is equal to 0, x1 is equal to 10. So in this graph, here is the line for constraint 1, 2, and 3. At dahil lahat sila is greater than the constraints, so ang feasible region will be in the right upper. So the candidates for the optimal solution will be these 4 extreme or the corner points. At dahil ang point 2 and 3 are pretty close together, let's be more careful and investigate every single point. So the coordinates at point 1 are 0 and 6 and 10 and 0 at point 4. We can also see here that they are 2 and 2 at point 2. For point 3, we can solve the two lines simultaneously. Multiplying the first equation by 2 and subtracting from the second, we have x2 is equal to 1.5 and x1. So, plugging these points into the objective function, we see that point 1 provides the minimum value of the objective function. So, the optimal solution occurs at point 1 with x1 is equal to 0 and x2 is equal to 6. And the optimal objective function value is 6. Now for standard form, since these are greater than constraints, we introduce surplus variables for the 3 constraints by subtracting S1, S2, and S3 from the left side and changing the inequalities to equalities. Substituting the optimal solution, we have surplus value S1 is equal to 0, S2 is equal to 2, and S3 is equal to 40. And as a result, only constraint 1 is binding because it has a surplus value of 0. And on the graph, we can see that of the 3 constraints, only constraint 1 touches the optimal solution point. So, ito na nga ika-calculate na natin ang shadow prices for the constraint. But before that, let's define what is shadow price muna. Shadow price is defined as the amount of change in the optimal objective function value per unit increase in the right-hand side of a constraint. So, para dito sa first constraint natin, kailangan natin i-increase ang right-hand side from 6 to 7 and i-determine natin ng amount of change in the objective function values as a result. So, the binding lines are x1 is equal to 0 and 2x1 and x2 is equal to 6. So, like I said, ang shadow prices for a constraint graphically, pag i-calculate natin siya, kailangan natin i-increase ang right side of constraint by 1 and isosolve natin siya with the equation of a binding constraint. And so, for the constraint 1, we increase its RHS to 7 and solve it with x1 is equal to 0, and since x1 is equal to 0, x2 is equal to 7. So, ang new objective function value natin is 7. Ang old objective function natin is mean z is equal to 5x1 plus x2. So, sasubtract natin ng old objective function sa new objective function. So, x1 times 0 is equal to 0. So, ang natitira na lang is x2 is equal to 7. So, ang old objective natin sasubtract natin sa new objective, which is z1 is equal to 5 times 0 plus 7 is equal to 7. So, ang z1 natin ngayon is 7. So, i-minus natin siya sa z6 sa optimal solution na given sa z1 natin. So, 7 minus 6 is equal to 1. So, that ang shadow price natin is 1. Computation for the constraint 2 and 3. Pero dahil they are not binding, mag-equal na siya sa 0. So, ang shadow price ng 2 and 3 is 0.